One's fine. That's it. All right. So remember from yesterday, what we talked about yesterday was the idea of growth and decay, and the ideas of A, B, H, K, what those values did to our graph. Remembering that A had to do with the concavity, concave up, concave down, what type of graph we have. B had to do whether it was growth or decay. H and K were our translations. Now, for today, what we're going to do is take a look at two examples. We're going to take a look at two of these examples now. The first one we're going to look at. Sorry. Okay, the first one we're going to look at. That's all right. We're going to look at a bacterial infection. So first of all, what's a bacterial infection? What does that mean? That sounds kind of gross, right? What is it then?
Infection.
Infection.
I know from bacteria.
From what?
It's like grows and spreads.
Okay, it grows or it spreads, so you're thinking of exponential growth right away, not decay. Very good.
Bacteria.
Is the bacteria involved, right? Is bacterial infection?
Keeps getting bigger.
Okay, you said it grows already, yeah? You got an example? Okay, give me an example. I think pink eye is one of the bacterial infections, actually. It's considered to be one.
Negative.
What's negative?
The bacteria.
It's a negative thing.
Yeah.
Yes. And you want it to become less and less as you go through and take treatment, right? Okay. So let's discuss what happens here. So imagine if you have a bacterial infection and you let it go untreated for a little while. Okay, if you let it go untreated. What it will do is follow this function. Now, this function here that I'm giving you tells us right away certain things. First off, we look at the B value. The B value is 2. What does that mean about this kind of a graph? Is it growth or is it decay?
Growth.
Why is it growth?
Positive.
Be careful.
Greater than 0.
Greater than 1. Remember, anything between 0 and 1, when the B value is between 0 and 1, we have exponential decay. So we have growth in this case. We have growth because it's greater than 1. Next, the 3 value is positive, and that's our A value. A is 3. Since it's positive, are we concave up or concave down? Up. I heard both. Up. Again, positive means the graph is concave up. Negative means the graph is concave down. And then finally, we've got these other things going on over here. And we talked about these quickly yesterday. Good. H and K. Well done. Now tell us. The negative 5, which is K. What does that do for our graph? Which way?
Right.
But K is up and down.
I give up.
K is up and down. Is it not working at all?
I don't know what's wrong with that
He
thing.
doesn't know how to put it in the staple.
I put it in the staple.
Just sit down. We'll do it after, Anna. We'll do it after. Calm down. So the negative 5 that we see here is our K value. But the K has to do with the vertical shift. Remember yesterday when we looked at this part right here, where we graphed these 3 together and we were able to see that there was an asymptote for each of these, the horizontal asymptote. For all 3, this asymptote was at 6, at 2, and at negative 3. It's going to be the same thing again today. So what you're going to see for this kind of a graph, already we're going to know that there's going to be some sort of an asymptote down at negative 5. And there's going to be our horizontal. Where is it? Why did I skip the problem before? We did it yesterday. We had the class day yesterday. Look at your notes. You must not have taken them. Now, the other thing we want to think about, again, it's exponential growth for short. So it's going to be some sort of a shape that looks like this, because it's growth. What about this H value? What does that tell me? The H value up here in the exponent.
Horizontally up.
Horizontally up.
It's going up horizontally.
Horizontal means left to right, doesn't it?
The thing is going to be 1 above the x-axis.
Up hours. You're putting the 2 things together now.
It's gonna go vertically. It's gonna shift.
Which way?
I won't tell them. Right.
Plot this way.
Left.
Remember it's x minus h? Go back to your standard form, people. Standard form tells us this.
Oh my god.
Okay? Well, you said vertically and you were going like this. He said horizontally and he was going like this, which is both backwards, okay? Again, how do you remember horizontally? Horizon is this way. Horizontal, horizon.
And vertical is
vertical?
an elevator. Oh, I don't know.
Or what's the basketball term?
Jump.
You jump.
I don't know about
Should jump.
I don't know
Should
about
jump.
basketball.
So vertical is if you're standing still and then you jump from there, how high off the ground you go. Normally, you put your hand here, or you hold like a magnet of some sort, and then you jump and smack the wall at the top to see what your vertical is. But it's without running. It's just a standing still jump. So it might help if you've played basketball. If not, just remember vertical is up and down or an elevator. That's fine. But horizon is the easy one to remember. Horizon is this way, horizontal.
Plus the Z, which
Plus there's what?
the Z, you know, Z.
Yes. You remember that? Oh, yeah, it's good memory. Remember we did this when I wrote the word horizon? And I wrote it like that, horizontal. Think left and right. And then the word vertical, there's an I in vertical.
Yeah.
Not that.
But it's an iron.
Yeah, that's why I remember we said that, like, but there's also an I in horizontal. Anyway, so we have a horizontal shift, and this horizontal shift will be to the left 1 unit. To the left 1 unit. Again, I know that because it's x minus h. And my h value then becomes -1. Okay, my h value is -1 because I see a positive 1 up here. I see a positive 1, which makes the h value -1. All right. With that said, we want to go ahead and graph this. And we want to graph it on the interval -3 to 3. And then discuss the characteristics of the graph. We're going to do those two things. What I'm also going to have you guys do on this is graph on your calculator as well. Okay? So you can start by doing that if you want to, or we can start by going over it first. Doesn't matter either way. We can do it by hand first, and then we'll check on our calculator, or vice versa. Doesn't make a difference. What I want you to start with, though, is this. Remember from the M&M lab the other day? Remember the A value was our starting point? And if you started with 1 M&M, and we kept growing and getting more and more M&Ms, that was our A value. And then we started the next part of the lab with 150 M&Ms or 160, or many of were, and that was our starting value. This A value is still like our starting value, but now we have a shift going on. So what I want you to do to start this problem is put like an open circle at the A value. And this is like our starting value, or this is like our, remember we called it the original, with quotes around it, original y-intercept. Okay, the original y-intercept. I'm sorry? No, it's not a hole. I'm just putting an empty circle there for a reason, because in a minute we're going to get rid of it. It's not actually going to be on the graph. This is not a point. It's just like a, you know what, if it makes it easier, Rosie, put an X across there then, okay? Just so we're clear. Put a little X on whatever the original y-intercept is. Because we're going to shift it in a minute. It's not going to be our actual y-intercept. Okay? You got to watch the video. Okay? It's not,
But no.
it's an X spot. It's not the variable X, remember.
Oh.
It's a spot. Okay? So we're putting a spot here. Now, the shift here is left 1. The shift here is down 5. So start with that spot you have marked. Go left 1 and down 5 and put a point. Okay, go left 1 and go down 5 and put a point.
Go left 1 and down 5.
Oh, wait. What's that?
I just gave very clear directions. Are you listening? You need to listen. I said, go to the starting point, take your shifts, go left 1 and go down 5.
Yeah, I get that. Why are we starting at 3?
Because remember how in the lab 3 was like our y-intercept? 3 was like our y-intercept or our starting value? It's the same idea now. This is still our starting value, but we have to shift. There's some sort of a translation. So it's no longer going to be our starting value, just like parabolas. Remember the parent function for parabola was this. And it looks like that the vertex is at the origin. But when we translated it, that vertex would move. So we're doing the same thing again. Okay, we're doing the exact same thing again. So we start at this point right here, which is not on our graph at all, but all we do is use it as a starting point. We go over 1 because h is -1. We go down 5 because k is -5. And that's one of our points already. This is an easy way to determine one of your several points you're going to need to graph. Now another way you could have determined that point is just by plugging in -1 for x. Right? Because this point is clearly -1 comma -2. That's what the point is. So if you had just plugged in -1 in for x, or in this case t, if you plug in a -1 here, you will end up getting -2. So you can always just make a table of values and do it that way also. Okay? Now for this kind of a problem, once I've marked that off, I don't need it anymore. Okay, so I'm going to erase that spot there, and I'm just going to use normal tick marks. I don't need that x spot anymore. Now, the next thing I want you guys to do is to be able to find the y-intercept. How do you always find a y-intercept? Set x to 0. Well, there's no x here. T to 0. Very good. Remember, the independent variable is normally x here, right? But we're talking about time, so we call it t. So we're going to set t equal to 0. When I do that, I'm doing n of 0. I'm taking the function n, evaluating at 0. We get 3 times 2 to the 0 plus 1 minus 5.
So you get -30.
You made a common mistake. You're not multiplying here.
That's what I did.
I'm not multiplying.
You get
That's
oh, one.
it's subtraction.
Yeah, one.
1. Okay, again, this is 2, because this is really 2 to the 1, which is 2. 2 times 3 is 6, and it's 6 minus 5, or just 1. Okay, just 1. So our y-intercept in this case is 1, which makes sense, actually. Think about bacterial growth. It's got to start with one bacterium at some point in time, right? And then what happens to that bacterium? It grows, and it multiplies, and it, it goes through its, what are the phases you learned in biology?
Oh, yeah, last year we did.
What stage is
You have a
it?
really good biology teacher this year, so I know it's not your teacher,
What?
it's a new
What?
teacher.
Almost got it.
Remember in biology talking about, like, I think it was like metaphase and stuff?
Oh, yeah, metaphase.
Prophase, and it has to do with amoeba.
Anaphase.
Yeah, it's similar to this here. Bacteria grows in that fashion, so it starts with 1, and it starts to like, asexually reproduce. Okay, it reproduces itself without a partner in a sense. Hey, what?
Biology last year.
How did I get it?
Yeah.
I said it equals 0. I said, how do I find the y-intercept, right? I said x is 0, but x is really t. So we set t equal to 0 to find the y-intercept.
Me, I'm doing just so you
Okay. Do you know any Spanish or are you just messing around? You can't help.
I don't know. I don't talk Spanish. I only talk English.
Speak. Okay. You don't talk English, you speak English.
Yeah, that's it. Like I said, I don't do that either.
Apparently not the best, huh?
Yeah.
Now, let's go back to the problem. We've got 2 points here, okay? We've got 2 points, you're going to have exponential growth. So right away, the shape of the graph will look like this. We have a general idea. But I don't really know too much more about it, so I can do 2 things now. One of those things is easy. We can just simply graph it. The other thing is to make a table of values. And the table of values, you can use your calculator for as well. So if it helps you and you want to make a table of values, that's fine. But let's go ahead and graph it and keep in mind the interval that we're graphing on. Okay, so let's go to our graphing calculator now. Let's all go to y equals, please. If you have your plots on, please turn them off. Remember we did those the other day?
Yeah.
So if plot 1 is highlighted for the statistics stuff we did, for the data for the M&M lab, please turn it off. Okay? Go up to it and hit enter. If it's highlighted, move up and hit enter on it. Okay? Alright, so let's plug in our function. We've got 3 times 2 to the, how do I put the exponent in here? Very good. In the parentheses, x plus 1, close the parentheses, minus 5. And again, our function was 3 times, because I don't put mine on math prints ever. You guys can change that if you want to. I don't like math print. It's very misleading. If you go to mode, hit mode, and then hit up. You see math print or classic anywhere? And then hit the button up, or go all the way down the bottom.
So at this point,
You guys see math print or classic? You want to go to classic then. It's only on T84s that does that, so don't worry if you have an 83. And the 84 does the math print or the classic. Now, what were my intervals to graph this on?
3.3.
Negative 3
negative 3.
to 3. So go to your window, everybody. X min, negative 3. X max, positive 3. I don't know much about the Y min and max just yet, so I'm going to leave it as negative 10 and 10. And then just hit graph for now. And we can change it in a minute, we'll see that we're going to do that in a minute. So we get the same general idea of a graph right away. Negative 5, 1, 2, 3, 4, 5. There's my horizontal asymptote, which fits in perfectly. Notice again, perfectly.
I think that the paper is affecting my calculator now. I don't do much.
Yeah, it's a little control there.
Yeah.
Oh, it's because you look at your equal signs. See the equal sign? It's having highlight. You turn it off.
Oh, I thought you said
Turn your plots off. You're getting plots the thing above. Those things are the plots.
Oh, okay. Thank you.
And change your window setting. I went back to 6. Yes. Y-axis. Because you didn't change your window settings. Your window's got to be -3 to 3 for x. Who just did that? Your window, look at x min, x max. Make it -3 to 3 instead of -10 to 10.
Mine
Got
doesn't
it?
look like that.
Okay. If yours doesn't look like this, please take a look first. Make sure your function is correct.
I mean,
And
no,
second, hit window and take a look. Make sure you have -3 to 3 now.
I'm talking about me sketching it.
Okay. Well, we're going to sketch in a minute. Hold on for a minute. If I really want to encompass this whole graph, I need to realize that this is going off. That's going to go off forever in that direction. So what I really need to do here is really change my Y max. I need to go a little bit higher here, right? So let's go back to our window setting. Hit our window setting and go to Y max.
20.
Let's make it like 30. I think we're going to need a little more. Let's try 30. I think we're going to need 50 in the end. But for now, let's try 30.
Can we ever put infinity?
Can you put infinity?
Yeah.
If you did, what would happen is, think about it.
Then
You would be zoomed so far out, you wouldn't see anything. It would look like a dot. Okay? So 30 works pretty well, right? If I change my Y max, again, here's my settings in case you're wondering. I change my Y max to 30, okay? Leave this as -10, you keep those as -3 and 3. Now, the question I want to discuss now is this. We've graphed this from -3 to 3. But for this kind of a problem, think about it logistically or realistically. It's a bacterial infection. So, for these problems, what did the x-axis represent again? What did we have instead of x in this problem? T, which represents what?
time in hours.
Time in hours. Very good. Time in hours since the infection, right?
Yeah. No, it says after the infection.
After the infection, yes. Time in hours after the infection. Can I say, Owen, you got sick and it's been -1 hour since you got sick. Does that make any sense?
No.
It doesn't make sense. I could say it's been an hour since you got sick, or it's been 2 hours, or 3 hours, right? But I can't say it's been -1 hours. So these values over here, even though they're graphed, they really should not be part of my domain. My domain for this problem is really from 0 all the way to positive infinity. That's what my domain for a problem like this is.
6 minutes.
So all I really care about is where I started, which was with one bacterial infection or one bacterium, and then where I'm ending up. Okay? Now, if this kind of a problem said, how many bacteria do you have after 20 hours? After 20 hours, what would you do?
You would go to 20. No. Wait. Yeah. Try to.
0 to 20.
Oh, you would plug in 20 into the graph.
Yeah, either plug in 20 or just plug it into your table. If you wonder how many bacteria, so let's say at the start, at 0 time, we had one bacterium, which is what we said. We started with 1. After an hour, after 1 hour, we have 7. After 2 hours, we have 19. But what about after something like 20 hours? I don't want to do that and go through it all the time. So that's where you use your table. Now, notice for this part,
Happy birthday. Happy birthday.
that we have 6.29 times 10 to the 6 here. Okay, this here is 6.29 times 10 to the 6. What does that really mean, though, times 10 to the 6?
Oh, it's scientific notation.
Good, scientific notation. So there's really 29, 1, 2, 3, 4. I take this decimal and I move it over 6 spots. There's 2 spots, here's the other 4. So really, take a look now. You have 6 million bacteria if it's not treated after only 20 hours. Have you ever heard before or seen, anybody watch, what's the show on Discovery Channel? Where the guys in the wild?
Oh, I think on the one.
Man versus Wild? Man versus Wild. I forget the guy's name, whatever. So, there are some episodes, though, where he'll, get cut or something. And he'll say something like, I have to sterilize it right away or else it can get infected. This is a prime example of something like this. A friend of mine right now is in Costa Rica, and he's doing a surf tour down there. And he was surfing and he caught some coral reef. So he got some coral reef cuts on, and reef is really, really, really sharp, like razor sharp. And he got a lot of cuts on his arm when he was surfing at one point. And he actually got some stuff embedded, part of it actually stuck into his arm.
Ew.
And he was taking a picture and he put it on Facebook the other day. And I was like, dude, are you an idiot? In 2 days you're gonna be dead if you don't get this treated. Coral reef is very infectious. And if he doesn't treat this right away, the bacteria is going to spread, and he's going to end up like losing his whole arm. If not, he's actually going to kill him. You can get gangrene, it can get swollen, it can be real bad.
At
Yeah.
the end, he'll be able to cut off his arm and still serve.
I don't know, your
That's not a
arms,
movie.
your arms are a lot of balance in surfing and skating. Think about it. When you surf or you snowboard or you skate, your hands are up out. It's to stabilize your balance. That's why you use poles to ski. So without an arm, that's going to be a lot tougher to surf.
But what about that girl that lost her arm?
I mean, it's a movie, but
It is based on a true
I'm sure it can happen. I'm just saying it's very good. I'm sure it could.
Then,
I mean, you know, it's not safe, right? Think about it. It's really unsafe. All right, let's go to the next problem. Let's take a look at the second one now. At the bottom of your page. Can I get a reader for this one, please? Amber.
the half-life of a radioactive element is given by the function n parentheses t n parentheses equals n
N0. It's N naught. It's called, but just say N0.
n naught.
Yeah, you can say
Okay,
N0.
n0 parentheses 1/2 parentheses t over t star.
T over T star. Okay. So we have this condition to start. The half-life of a radioactive element is given by that function. Now, it tells us that N of T is the amount of the substance at any given time. N0 is the initial quantity, or the initial amount of the substance you have. T star is the half-life of the element. Okay, that's our conditions. Next, imagine, who knows who Doc Brown is, by the way?
Doc Brown?
Doc?
Best doctor.
No, everybody forgot who Doc Brown was. First period, one person got it, and everybody was like, oh, yeah.
Those are
Yes, it's the dude from Back to the Future with crazy hair. You guys ever seen Back to the Future?
Yeah.
I've seen.
If you haven't, it's a funny movie.
I seen Bill
It's pretty cool.
Yeah.
It's a movie.
Remember Marty McFly is the main character?
Oh,
Marty McFly is played by Michael J. Fox. The guy that has Tourette's now. Everybody knows him from that, even though he's a very famous character.
the poke pad to
This whole thing is Doc Brown. In the movie, Doc Brown steals a radioactive element, which is called plutonium. Okay? He steals plutonium so that he can run the time machine. Remember, the time machine is the car. It looks like a Lamborghini. It's actually a DeLorean. It's named the car. So he has the DeLorean that he's created a time machine out of, and he needs a radioactive element. And if you remember, he steals the radioactive element from like terrorists, from like Afghan terrorists or something in the movie. That's what it is. And theoretically, radioactive elements have half-lives. So in the movie, they don't actually do it. But I thought about this the other day when I was making the problem. Really, what would happen here is that even if you stole 100 grams or kilograms of this radioactive element, after a certain amount of time, it wouldn't all be radioactive anymore. It's the half-life. So what I did was I looked up the half-life of plutonium-243, and it turns out that it's 5 hours. So after 5 hours, only half of the substance is radioactive anymore. So what we're going to try and do is figure out if he started with 10 kilograms of this plutonium, and the car takes 3 kilograms to have it run, how much time has gone by, or how much time can go by before he has to use the plutonium after he steals it. So he steals it, but he's only got a certain amount of time to use it, or else it's going to run out. That's really what's going on. Okay, so we're going to try and figure out that time value, the t value. So we're going to be solving for that little t now. It's going to be a little bit different. And we're going to do it graphically.
So the half-life is like what we did when
Yes.
you told me to
Halfway to the door.
and then okay.
Absolutely, that's it. Yep. And the idea for radioactive elements is that it will never go away. That's why radioactive elements are so destructive. That's why when things like an atom bomb is dropped and all the radiation that's there, it lasts for a long time. The plants are radioactive for a long time. People get some sort of morphing of their body or mutations that are not genetically likable. Not things that you want to have. Not like powers like X-Men. It's not like that. So we've got.
Why wouldn't you want to have powers like that?
You would, but I'm saying the mutations that come about from radiation are not like that. Those are movies. Those are not real things. You can't get like powers. You get like a third arm or something. It's not good stuff. And it's usually like stuff that can kill you. All right, you've realized that plutonium requires a half-life of 5 hours. So let's underline that, please. Half-life is 5 hours. That's important. What else is important in this problem? Yeah, what do we have to start with, Jose? Good, we got 10 to start with. Okay, 10 to start with, be careful. And what do we want to know how many we have left at the end? 3. Okay, when there's 3 left, the question is here. right, so let's write down what we've got. We've got T star is 5 hours. My half-life is 5 hours. N0 is 10 kilograms. Again, T star is 5 hours, N0 is 10 kilograms.
What?
Because the variable that, you can use any variable, but it's a half-life. A half-life is time. But I've already used T, because T is part of the function, right? Do we have a T up here already? So if I made a T over T, would that make any sense? So I had to indicate that it was something beyond just a time, but it was a half-life, which regards time. So I use little t, but put an asterisk. It's a mathematical acceptance that you've come up with over a long time. So even if I'm sorry, you know how in multiplication you can say, right? Does that make a difference there?
No.
It's an understanding that these are all the same, right? When you do more of this, you're going to use this thing like star or something with a star next to it. Just indicates that it's a time, but not necessarily the time we're looking for, but some other time, which happens to be 5 hours. It's a given quantity. It's like a constant like A or B or C there, but instead of calling it A, B, or C, we call it T star. Okay, so to answer your question, Marcus, because I wasn't answering because I was talking, this is a star. Okay, not an X, it's a star.
Asteroid.
So we've got T star or T asterisk, fine, equals 5 hours. N0 equals 10 kilograms. Asterisk. Now, we want to know when there's 3 kilograms left, right? So let's first of all plug these two values into the function. Let's write the function down. That's what we should have when we just plug in the numbers. Again, all I'm doing right now is taking our 5 in for T star, and our 10 is going in for our initial condition. Okay, so we've got an initial condition of 10, we've got a half-life of 5 hours. This is a tough problem though, because it says, determine when you have 3 kilograms left. When you have 3 kilograms left. So, which variable, and take a look at what's left. We have n of t as one variable, and we have t as the other variable. Which variable are we solving for? And which variable do we have?
We have n.
We have n. We have n. We have, remember, look at n, guys. N is the amount of substance. N is the amount of substance. And we're told that we have 3 kilograms left. So instead of n of t, this is really a 3 now. Okay, that's really a 3. Now, we cannot solve this. We cannot solve this by hand. Just yet. We'll do it next week. We'll determine how to solve this by hand. So the way to solve this problem, though, is to take a look at the graph. Let's open our graphing calculator, please. Go to Y1. Clear out what you've got. And knock it off, guys. Seriously. I'm getting on my nerves. 10 times, parentheses, 1/2 to the, what's the power again? T over? Come on, people. We gotta write stuff down. We just wrote this. T over 5. Let's go. T over 5. Now, I'm putting it as x over 5 because we don't have a t here. Remember your parentheses. 1/2 is a fraction. It needs to be considered to be a fraction. If you get the parentheses, it will not work the same. Same thing with t over 5. T over 5 is a fraction. It needs parentheses around it. Now let's hit zoom 6, please. Zoom 6. Now, take a look at this problem. First of all, what quadrant does it look like it's in?
Second.
First one.
First. Remember, you order the other way. It's always 1, 2, 3, 4. Not 1, 2, 3, 4. Okay? Counterclockwise. 1, 2, 3, 4. It's in the first quadrant meaning. Now, if I zoom out a little bit, though, I'll see that it's not. It goes on forever this way, and it also goes on like that. It's never going to cross, but it goes on like that. What was the amount of plutonium we had to start in this problem? 10, right? 10? And take a look. Isn't the y-intercept 10? Because there were no shifts in this problem at all. There were no shifts. We want to know when there's 3 kilograms left. Well, this is 10, 9, 8, 7, 6, 5, 4, 3. Here's 3, right?
So do we do a little estimate then?
So we can do an estimate, sure. Let's do an estimate first before we get to this. So we're trying to figure out what is the value of the time right here. When is it going to have 3 kilograms left? So we can start by just doing an estimate. That's one way to do it. To do that, we would press trace, and and then go over, and keep going over until we get to around 3 for the y value. Look at your y values. 3.5, 3.4, 3, 2, 1, 07, 9, that's closer. This is the closest so far. It's around 3, right? See this? But as mathematicians, you don't want to estimate stuff like this. You want to know exact values. You want to round and say, oh, it's around 3. Let's find out the exact value. So, this seems like a good estimate. So, after about 8 3/4 of an hour, not 3/4, 7.5, about 8 3/4 of hours go by, you have 3 kilograms left. Good estimate. Now let's find the precise value. Go to your y equals. Go to y2, please. What's the quantity of plutonium we want to know? 3. We started with that. You want to know is when it's 3.
So you put the same
Just
thing
type in
with
3.
the-
Type in 3. No, just simply 3. Like exactly 3. Nothing else. That's it. Now graph it together, please. What are you going to notice you have here? And where does it intersect? At 3. So what can we do now?
We can go to the line.
How do we find the intersection on these calculators?
Oh, you go to it's an intersect thing.
Yeah, it's called intersect. Absolutely. But where is it on the calculator?
Y-intercept.
Second, delete.
Second, not delete. Nope.
That's what I said.
Second calc.
Second calc. There it is. Second, and then hit this button right here, calculate. Now, there's a function on here called intersect. Number 5. Calc is trace.
Oh.
It's above it. Number 5, press next, or intersect. And what you want to do is move over until you get near the intersection point. Just get to the general vicinity of the intersection. It's just like we did earlier. Very good. Enter, enter, enter one more time. And take a look. What's the y value now? It's exactly 3. Earlier we were getting 2.98, 3.07, but now it's exact. And what's my time? 8.68 hours. And earlier, when we did this, we had about 8.72. So it is different. It is very different. Okay, we're talking about 0.04 hours. I mean, if Marty McFly didn't hit the engine fast enough, he wouldn't have made it happen, you know? It really is a big difference in time. So 8.68 was our actual value for this problem. So again, what did we do here? We want to find out when the problem, or when the exponential decay had 3 kilograms left. So we put 3 into y2 and figured out where that intersection lies. One day.
Would we have to say like if it's a positive growth or?
Yeah, a lot of your problems I'm going to ask, like, is this growth? Is it positive growth? Is it concave up? Is it concave down? All the stuff that we talk about in the beginning, you'll usually be asked that kind of stuff. Okay? All right. So if you were doing this problem as a pre-response and it only said find the time, I would personally do this. I would draw a graph as my sketch. I would draw a line like that. I would draw an intersection, put a dash like that, and say this is time 8.68. That's all you really need to show as evidence, because that's all you're really doing. Okay? Just a sketch. All right. What we're going to do now is start concept 54. And we only have about 15 minutes left. We're going to go ahead and begin 54. 54 is applications of growth and decay. It's similar to what we've been doing, but all word problems now. And your homework tonight is going to be doing just 53. And 53, what I want you to do, and I'm not going to give you just yet, but I'll show you. For 53, what I would like you to do is give me some examples of graphs. So for example, you're going to have just 4 different graphs to do. And you can use your calculator to help you, but I want you also to be able to do things like find your y-intercept, use the vertical and horizontal shift, show the asymptote. So you can use your calculator, it's not a problem at all, but you got to go through these 4 graphs. That's your homework for tonight. That's concept 53. Okay? We're going to start 54 now. Okay, we're going to start 54. And I'm not